Welcome to Guru Brahma classes for JEE and NEET. Good morning to one and all. So today's topic is hydrogen spectrum. Already in the previous video, I described about what is hydrogen spectrum. In this, we are discussing the formula to calculate the wavelength, to calculate the energy, to calculate wave number of the spectral line released in the hydrogen spectrum. So we are deriving a formula, Rydberg formula, how to derive that and how to derive the formula to calculate the energy of the spectral line, wavelength of the spectral line and wave number of the spectral line. So let us see that. First of all, from the Niels Bohr atomic model, we have studied that when electron undergoes transition between any two energy states, let us take these two are energy states. These two are energy states. This is 1, 2, for example, this is lower energy state and one is higher energy state, whatever it is. For example, this is initial state, this is final. Considering this as 2 and this as 1. So what will be delta E? E means when an electron get de-excited or when an electron get excited. How much amount of energy it is absorbing, how much amount of energy it is releasing, that is calculated as delta E. Delta E is equal to, so E final minus E initial, or simply final is taken as 2, so it will be E2 minus E1. Initial is taken as 1. Okay, final is not second energy level, but it is 2 representation, that's it. So the difference in these energy levels gives you the amount of energy absorbed or amount of energy released. When it is moving from lower energy to higher energy level, it is absorbing. By absorbing energy, it moves to higher energy level. By releasing energy, it moves from higher energy level to lower energy level. Right? The difference is given by delta E. And when we have calculated formula, when you have derived a formula to calculate the energy of stationary state, that is given by energy of the electron or energy in the nth stationary state is given by minus 2.18 into 10 power minus 18 joule per atom into Z square by N square. This is the formula, right? So this is simply, we can write it as minus 2.18 into 10 power minus 18. So you can write it minus RH joule per atom, as it is hydrogen atom. So Z will be equal to 1. So simply you can write it as 1 by N square, energy of the electron in the nth orbit or nth stationary state. What is H here? What is RH? RH is Rydberg constant. We have Rydberg constant as 109,677 per centimeter. That is expressing Rydberg constant in wave number. Here this is Rydberg constant expressed in energy, joule per atom. So what is RH here? It is equal to 2.18 into 10 power minus 18 joule per atom. Joule per atom. So this is also Rydberg constant, but this Rydberg constant is expressed in energy, in joules per atom. Okay. So this is the amount of energy possessed by an electron in the atom. It is the energy possessed by an electron in a particular energy state in an atom. Okay. What is the amount of energy possessed by an electron when it is at infinity distance? This is infinity distance. Consider. It's not under the influence of this atom. The amount of energy possessed is E infinity is equal to 0. What is that? At infinite distance, what is the amount of energy possessed by the electron? 0. When it is coming to the atom, when it is coming closer to the atom, in any of the orbit if you take, when it is coming into the atom, it is releasing some energy, and the energy possessed by electron in an atom will be negative. That is how the electron possesses negative in an atom. In any particular energy state, it will possess negative energy. Okay. So let us take E initial. Initial we have taken it as E1 minus RH into 1 by N1 square. E2 final. 2 is considered here as final. Then minus RH. RH means Rydberg constant, hydrogen atom. Okay. Rydberg constant 1 by N2 square. We know that delta E is equal to E2 minus E1, right? Then what will you write? Minus RH 1 by N2 square minus of minus RH 1 by N1 square. That is equal to, minus into minus becomes plus. That is RH 1 by N1 square minus RH 1 by N2 square. That is equal to RH 1 by N1 square minus 1 by N2 square. What is this? Delta E. Delta E. So during absorption, in the case of absorption, so when electron is absorbing energy, it moves from lower energy state to higher energy state. That means N1 will be less than N2. Okay. During emission, that means here this is N1, for example N2, N1, N2. Here is the electron. By absorbing some energy, it has moved into N2. So N2 is greater than N1. That means N1 is during emission. During emission, initial, see, emission means here from here to here it is coming. Okay. So this is higher N2, but here it will be N initial. From here it is moving to, this will be final, right? So during absorption, as N1 is less than N2, this delta delta E will be positive. What will be this? The delta E will be positive, representing that it absorbing. During emission, N initial will be greater than N final. N initial will be greater than N final. So N initial, if it is greater, so delta E is equal to RH 1 by N initial square minus 1 by N final square, right? N initial is greater. If N initial is greater, automatically delta E will be negative. N initial is greater, okay, automatically delta will be, E will be negative. Negative represents that energy is released, emission. Okay. So next coming to, so what formula we have derived? Delta E is equal to RH into 1 by N1 square minus 1 by N2 square. And from Planck's quantum theory, we have studied that E is equal to h nu. E is equal to h nu. Nu is equal to E by h. Frequency is equal to energy by Planck's constant. Here if you see, delta E is also energy. Higher energy minus lower energy gives you energy. Overall, delta E is nothing but energy. Delta E is nothing but energy difference gives you energy. If I want nu, then what I can write? Nu is equal to energy by Planck's constant. So energy is this formula, right? So RH by h into 1 by N1 square minus 1 by N2 square. So nu is equal to, on calculating it, what you get, you are finding here 3.29 into 10 power 15 into 1 by N1 square minus 1 by N2 square. Frequency will be in hertz, right? Frequency is in hertz. So this is formula to calculate frequency. So either you can use this one, RH by h into 1 by N1 square minus 1 by N2 square, or calculated value also you can use. The next one is how to calculate wave number. What is that? Wave number. And we know that E is equal to h nu. E is equal to hc by lambda, and E is equal to hc into 1 by lambda. If I want 1 by lambda, what I can write? E by hc. E already we have seen, E is nothing but RH into 1 by N1 square minus 1 by N2 square. Now E is this one. HC also we have to write now by HC. If you use RH value, RH already we have seen 2.18 into 10 power minus 18, 2.18 into 10 power minus 18 joule per atom, by H 6.626 into 10 power minus 34 joule into second, into 3 into 10 power 8 meters per second, into 1 by N1 square minus 1 by N2 square. On calculating this, what do you get? 1.09677. Okay. What value you get? 1.0677, right? Into 10 power 5 per centimeter into 1 by N1 square minus 1 by N2 square. So when you multiply this, 109,677 approximately per centimeter 1 by n1 square minus 1 by n2 square. So this is again called as RH, Rydberg constant. So this Rydberg constant is expressed in what? This Rydberg constant is expressed in wave number 1 by lambda. 1 by lambda is also called as a wave number. What is 1 by lambda? Wave number. Wave number units per centimeter per meter. Here in what units we have calculated? We have calculated in per centimeter. Okay. So what is this RH? RH is what? Rydberg constant in expressed in wave number units, expressed in wave number units. So wave number nu is equal to 1 by lambda is called as a wave number. Understood? So 1.0966 into 10 power 7 per meter. If you convert it into centimeter, then what do you get? RH value will be equal to 109,677, okay, per centimeter. Right? So Rydberg constant value is not same for all the elements. It is not same for all the elements. For hydrogen-like species, already we have studied that in another way you can write. For other species you can write nu bar is equal to 1 by lambda, that cannot be written as RH into Z square, RH into Z square into 1 by n1 square minus 1 by n2 square. This will be the formula. Why we are adding Z square? In the starting part, there is Z square. Actually, there is a Z square here, you see. Here you can find it. There is Z square here. As it is hydrogen atom, we substituted 1 in this Z square, this Z, and we calculated all these things. But when you are coming to other atoms which are having one electron, that is He plus is having one electron, Li plus 2 is having one electron, Be plus 3 is having one electron. These are all one electron species, but their atomic numbers are different. When their atomic numbers are different, you have to multiply with the Z square. So Rydberg constant is not same for all the elements. For hydrogen it is RH, but for other elements, one electron species, it must be multiplied with Z square. Must be multiplied with the Z square. We are finding here. And 1 by R value, you need to remember Rydberg constant. What is that? 912 angstrom units. At present in the competitive examinations, they are giving this value, or otherwise for the easy calculation you have to remember this. 1 by RH value, 1 by 109,677 per centimeter. You are dividing it. When you are dividing, that is 1 by 109,677 per centimeters. Okay, per centimeter gives you what? Per centimeter gives you this 912 angstrom units. So the first line in the Balmer series is also called as H alpha line, and its wavelength is equal to 6563 angstrom units. Right? So let us see. Already in the first part of hydrogen spectrum, I discussed what is meant by H alpha. right? So let us see once again. When electron is de-exciting from higher energy level, third energy level to second energy level, then that is called as H alpha. When it is de-exciting from fourth energy level to second energy level, then that is called as H beta. When it is de-exciting from fifth energy level to second energy level, it is called as H gamma. Sixth to 2, it is H delta. So for every spectral line, what will be there? There will be some energy associated. For every spectral line, there will be energy. For this energy, E is equal to H nu, or E is equal to Hc by lambda. For every energy, there will be some wavelength associated with it. For every energy, there will be some frequency associated with it. Okay. So here the spectral lines get closer when N2 value is increased. Right. Next, when N2 is infinity, what is that? When N2 is infinity, for any spectral line, what is this infinity? 1, 2, 3, 4, 5. In Rydberg formula, already we have seen mu bar is equal to RH into Z square, 1 by N1 square minus 1 by N2 square. We have N2 here, right? So for any series, for any spectral series, if N2 is equal to infinity, then that line is called as limiting line, limiting spectral line, limiting spectral line. That is that called as a limiting spectral line, right? Or which is also called as a last line, last line or limiting spectral line. It is applicable for any spectral series. 5 series of spectral lines we have seen: Lyman, Balmer, Paschen, Brackett, and Fun. For every series, it is applicable. Okay. Then let us see here, for example, coming to Lyman series, or whatever the series. First, let us go with Lyman series. So 1, 2, 3, 4, so on, infinity. 1, 2, 3, 4, 5. Okay. You will be asked in the Lyman series, spectral line with least energy. Least energy is also longest wavelength. Least energy spectral line will have longest wavelength. Why? Least energy. We know that E is equal to Hc by lambda. If E is minimum, then lambda will be maximum. What is that line? Least energy line is 2 to 1. This is E minimum line and lambda maximum line. Okay. Next, maximum energy difference will be from infinity to, what is that? From infinity to 1. So from infinity to 1, E will be maximum. Energy difference, infinity to 1. There is maximum energy difference. So infinity to 1 will be E maximum and wavelength will be minimum. So you will be asked the spectral line of least energy and maximum wavelength. Least energy and maximum wavelength. Or a spectral line having maximum energy and least wavelength. Least wavelength. For example, if you consider the same way Balmer series. Balmer series. The Balmer series 1, this is infinity. Okay. 4, 5, for example, 1, 2, 3, 4, 5. So, energy minimum will be 3 to 2 spectral line. So, lambda will be maximum. So, what do you write? N1 is equal to 2, N2 is equal to 3. If electron de-excites from infinity to second energy level, infinity to where? Second energy level, then that will be having energy maximum, wavelength minimum. That means N1 is equal to 2, N2 will be infinity. So energy maximum energy spectral line will be least wavelength spectral line. Energy minimum wavelength spectral line will have maximum wavelength. So the same applies to every series of spectral lines. Every series. So when N2 is taken infinity, then the wavelength will be limiting line, and you will find N2 taken as infinity. So the wavelength of all the spectral lines can be, the wavelength or wave numbers of all the spectral lines in all the series can be calculated using what? A Rydberg equation or Rydberg formula. Rydberg constant expressed in wave number is 109,677 per centimeter. Okay. So that is about derivation of Rydberg equation and explanation of Rydberg equation. In the next video, we shall see PYQ JEE main on hydrogen spectrum. Thank you for watching. We shall meet in the next class.